is titled Storage and Retrieval. And the so last chapter, last week, we talked a little bit about data models and query languages, and so now we're going a layer below that to talk about underlying how do you actually implement these. So in today's world, if you want to persist information across time, and especially persist it across server crashes, things like that, then you need to go to disk. And so that's one of the big challenges, which is how do you take information and organize it in a way that you have hopefully fast reads and fast writes and persist it on disk. And then Ryan, would you just let me know if there's anything in chat, if we need to pause, talk about questions or anything like that?
Sure, I'll stay on top of that.
Yeah. But everyone feel free. This is a discussion, and in particular here, I think I'm going to go a mix of, for some concepts, go faster, if it's something that I think maybe people are a little more familiar with, so stop me, slow me down. And then there's just a few tidbits in here that I just thought were really fun, and if I need to speed up, then you can also prod me and say, don't spend so much time on this one detail. So the author begins introducing things with a motivating example where he says, hey, what if you just had this giant ledger, and so every time you want to do anything, you just insert a row at the bottom. So this is a lot like a log file, just like system logs, web logs, whatever, where you're just always adding a row at the bottom. In this case, it's the concept of a key value. So there's some key, and then there's the payload, which could be arbitrary, any amount of any kind, any amount of data. So if you did this, then writing things would be very fast. And what you would do is, if you said, hey, I already inserted something for the key 1, 2, 3, 4, 5. If I want to change that value, I'm not actually going to update it. I'm just going to create a new entry at the bottom. And the convention is, if you have more than one key, 1, 2, 3, 4, 5, then you read the bottommost one, the most recent one. And then all the other ones are obsolete. So even if they're physically still there, they're designed to be ignored. And if you do this, you'll actually get really fast performance on writes, because you don't have to go looking for where to write. You're just writing everything, right there at the end. But the problem is that if you read from this structure, then worst case scenario, basically you're scanning through the entire table, the entire database from top to bottom. And so that's going to be linear time with the number of entries. So if you've got 1 billion entries, you got 1 trillion entries, then it just keeps getting slower and slower. So although nice and simple, that's probably not going to give you the responsiveness that you want. So I like this sort of loose terminology here, where if you add any kind of data structures, any kind of metadata, loosely we can call these indexes. Okay, like maybe there's other names for things that are more specific, but if we just loosely call them indexes, then the general pattern is, when you write something, you need to update this metadata. You need to update these indexes. And that is going to add some amount of cost to your writes. So what you're doing is, this log has a super fast write to begin with. You can afford if you make it 10% slower. But what you're trying to do is do that in a way that it tremendously speeds up your read performance. And then, of course, everything depends on the profile of your workload as to what types of optimizations might make the biggest difference. So if we were to talk about this chronologically, we would probably start with relational databases and then get into these other sort of log structured storage systems. I think the author kind of went this way because he's trying to sort of build up concepts from sort of simpler things to more complex. So we will certainly get to the relational systems, but first there's a tour through increasing levels of complexity with how do you take this simple idea of a simple log file and add metadata, add indexes to it in such a way that now you can actually improve read performance dramatically. So the first concept is hashing. Um, I suspect most people are familiar with hashing at some level, whether it's, in programming languages versus not necessarily in databases. But so the whole idea is that, if you can do a hash function that takes your key and turns it into a relatively unique value, then basically you can just look up against that hash value, and you can have a pointer that says, oh, instead of reading through this entire giant log file, if you go all the way to byte 6789, that's where you'll find the information that you want. And interestingly enough, you can actually build a viable system with just this. You just have a hash map, and it points to where all of your data is. The problem if you do just this vanilla system is that your log file is still going to just grow and grow and grow and grow. So a simple thing you can do is you break the log file into segments every so often, and you could theoretically keep them all, but it's still going to grow and grow and grow. And especially if you have a lot of updates, those old portions of your log file, they've got junk that's been deprecated. You don't really need to keep it around anymore. So then the idea is then you can do this compaction process where you say, hey, I've already overwritten the key 1, 2, 3, 4, 5 100 times. Those 99 other copies, I can remove them. So what I can do is I can just take these old files, make a copy, delete anything that's now, obsolete, and I'll have a much smaller log file in the process. Hey, while I'm at it, not only can I remove those obsolete entries, but since these are much smaller, why don't I merge them together? Because, on disks, you don't want tiny little files. It's more efficient to access, bigger chunks. And so now that gives us the concept of basically we've got compaction, and so you can have a system that's quite performant, where all you're doing is saying, I'm going to break my log file into chunks, and in the background, I'm going to have this process that periodically compacts the old log segments. So that's sort of our first level of, here's a system that there are versions of this that actually exist in the real world. We can implement this. So let me pause here. Any comments or questions?
I wrote this on the chat as well, but I mean, if you have an index pointing at the data locations, then why would you be writing to the end of the log file? You would just directly write to wherever the data is, wouldn't you?
Yeah, so this is where talking about logs first is kind of backwards. So the whole idea here is that when we talk about relational structures, we update in place, which is exactly what you're saying. It's actually, to me, it's the far more intuitive way you would do it, right? Why would you go and write something at the end when?
Yeah.
But disks, especially spinning disks, are very poor at random access. And because random access can be slow, and in particular, it's not just slow in terms of latency, in terms of how long does it take me to get one particular thing read or one particular thing written, because I'm waiting for the disk to come around and for the head to then, get to that spot. But the other problem is that the whole time that you're waiting for that disk to spin around and get to the right spot, you're also not doing anything else.
Yeah.
You're not reading anything else or writing anything else either. So it also affects throughput. So it's affecting latency and throughput. And so the fundamental principle of using logs is that you do a whole bunch of writes. So let's say I log 100 things, 1,000 things. I'm doing those sequentially, and I'm really maximizing the use of my disk for that period of time, because I'm just, doing this big sequential write.
Yeah, I think there was a database called Tokyo something. I think they were doing a system like that.
Yeah, so I would say the unintuitive nature of writing duplicative data is why relational databases were around for 20, 30, 40 years before people realistically started looking at the idea of we could actually get better performance by making more copies of the data.
Yeah.
Okay. But generally speaking, it's that write concentration, and then also the other thing is, because you know that these old log segments are read only, that they will never be updated, that gives you I don't know the right way to say it, but that makes your life simpler in terms of when you're doing the compaction. It's very easy, because what you can do is you can read something, you can write the new version of it, like when you're just deleting obsolete entries. And at no point do you have to worry about, is it going to change on you during the time it takes you to read this compacted and write it, because it's read only. And if you wanted, hypothetically, you could wait 5 minutes after you've compacted it before you tell people, hey, go point to the new compact one instead of the old one. And there's no harm, no foul, because it's read only. So it's those two properties, especially the read only gives you, I don't know what the right way to say it is, but that guarantee allows you to come up with ideas for how you do things that you can't do in something that's constantly changing.
Yeah.
Hey, Ted, this may be the wrong time and we can delay this till later on, but I was kind of curious how solid state drives figure into this, right? And whether they change the discussion. And I believe even with solid state drives, it's not true that it's completely random access, that you still have to read clumps of bits or bytes together, sort of thing. But I didn't have the time to look it up.
I don't know if anybody else here knows. I do not know SSDs, but I've read multiple times in lots of places that both reads and writes are actually accessing blocks within SSDs. And so in RAM, you can truly just say, write an integer at 1, 2, 3, 4, 5, and then write another integer at 6, 7, 8, 9. And it's kind of like the same performance as if you said 1, 2, 3, 4, 5, and then write something at 1, 2, 3, 4, 5, 6. You know, adjacent places, right?
Right. Yeah.
And it's not quite that free performance with SSDs.
That's my understanding too. Yeah.
Yeah.
Go ahead.
Regarding SSDs, when you look at their benchmark numbers, they'll typically show you different queue depths, which is basically how many tasks are backed up, and it's kind of prefetching them. And then you'll also see variations on the block size. And so you can see when it's fetching different attempted sizes of files, basically. And you can see how the performance changes when you change the size of the files that they're trying to request. And lots of little tiny files is still going to potentially bring it to its knees. And so another factor that SSDs are graded on is their IOPS, the amount of operations they can do. And so you typically want super high IOPS, and then you can kind of deal with small files well too.
Cool. Thanks, Ryan. Yeah, so the bottom line is, even if you switch to SSDs, to a certain extent, you still have these disk versus memory performance patterns. It's faster, it's better, but you still have that pattern apparently. All right, so we talked about simple, unordered, write only at the end log files. And so then we get to SS tables and LSM trees. This was new to me. I don't know about you guys. I had to kind of go through this material to really understand it. So the idea is that, okay, I just said the great thing about log files is you write everything right at the bottom and it's all contiguous. Well, if it's sorted, then obviously you can't do that. You can't just always write everything at the bottom, because if you have a Z followed by an A, you can't write the A at the bottom. The A has to go at the beginning. And so this talks about, well, how do we approach that? And so the basic idea is that if you have sorted files, mostly I'm still going to call them log files, although SS tables, technically they're not really logs anymore, because now you're writing, you know. But what you can do is, instead of every time somebody wants to write something, you immediately spit it out, right? What you can do is you can accumulate a certain amount of work in memory. And then after you've accumulated that work, you then spit out a big batch and you write that to a file segment. And the idea there is that you're not technically going to be appending to those the way you do to logs, but you're still doing this thing where you're doing a long contiguous write. So if I have, 50 megabytes that I've saved up in memory, and now I want to push it out to disk in sorted order, that write of 50 megabytes contiguously can be done very efficiently by disk systems. And there's gory details about how the controllers will sort of pipeline stuff and yada yada yada, caches, whatever. But so the bottom line is that the disk system can handle writing of 50 megabytes way, way, way more efficiently than if you issued 500 individual, 100K writes, for example. And so it's not quite append only, but it's still got that pattern of this read only, write in big sequential batches. So you got these SS tables. These are these sorted log segments. Then it goes into more detail about LSM trees, which is how you again, you have these multiple tiers. So in memory, author doesn't go into detail, but life's a lot easier in memory. So you can manage keeping things in order. There's balanced trees, and in particular, like red-black binary trees is a way in which you can insert things in any particular order, and you will get a balanced tree that has good, log and read performance. But you can trivially read records out of it in sorted order. So that's what that's taking care of. And so then the idea is that basically you keep a decent chunk of stuff in memory, you periodically write stuff out to disk, and now you've got sort of two things going on. So one is, before, when we were compacting, we didn't care about order. Now we do care about order, but if you're familiar with merge sort, or if you've ever had two piles of papers that were both already sorted and you just wanted to sort the collection, there's a fairly efficient algorithm where you just say, okay, here's a bunch of A's. The first item I have on the second stack is a B, so I can just skip ahead straight to the B's, insert that, and interleave those two. So it's a very efficient linear order algorithm. The other thing that was mentioned is that in the traditional hash map world, because any record can be anywhere, you need a full map that tells you how to find every single item. Well, now that you know that things are sorted, let's just use numbers instead of strings. So if you have a pointer that says, here's where item 1,000,001 is, if you're looking for item 1,000,005, you don't necessarily really need a direct pointer to 1,000,005. You can just go to 1,000,001, and then you can just kind of walk sequentially through the list, because it's sorted and it's going to be close. So that's considered good enough, and so that's where this comment is, that you can have partial indexes. You don't have to have an index for every single entry. You just sort of have periodic things that says where things are. And then there's a trade-off, because obviously if between 1,000,001 and 1,000,005 there were 50,000 entries, actually, not just a handful, well, then I would have made the mistake, and I would have had to linearly walk through 50,000 entries before I got to the one that I actually wanted. So you need, kind of balance that, but that's kind of a cool optimization. All right, so the idea here is that writing is, you sort of have this delay action happening with writes, because it's sort of going in memory and then it eventually. So write performance is as good, if not actually better, than if you just have an ordinary not ordered log table. And then reads, you've got a little more overhead. You've got this in-memory part, and then you've got these other things. But one of the key things to understand is that for just handling user requests, things are probably really good. Where things get a little bit dangerous is we now have these two background processes. We have the compaction process, okay? and we have the process that says, let's take a chunk of things that are in memory, write them out to disk and remove them from memory. And so, you know, one of the comments later on is, if you have really high volumes of activity, you can get to the point where those background processes can't keep up. And so that's where things can get really dicey, and your failure mode can be a lot more unpredictable. Whereas we'll see for relational, you actually could run into a bandwidth issue, but it's actually much more predictable. What happens is just response time gets worse. You know, you can't have sort of this overflow kind of a situation. All right, let me pause here. So this kind of took me a little while to wrap my head around how the ordered files can work, since obviously you're not able to write to the end of them. You always have to write. So any questions, any comments?
I have a question. So they're both ordered, correct? But the SS tables are just ordered in a different way, because the whatchamacallit, the hash tables had the indexes as well, but then how is that, basically what's the difference between the two?
So the hash tables are not ordered at all in any way.
Oh, so
okay,
what's an index for a hash?
So sorry, your in-memory hash lookup is ordered on the hashes.
Oh,
okay,
gotcha.
but the disk storage is just completely sequential. No sense.
Okay, so difference between the disk storage and then the in memory, right?
Yeah.
Okay.
So if you insert whatever cherry, banana, apple, then they just go in the log cherry, banana, apple. Whereas when you have an LSM tree, and if you put cherry, banana, and apple in on the physical disk file, it's going to be apple, banana, cherry. It's going to be in alphabetical order.
Mhm.
Okay, so what has to happen is it has to build up a bunch of stuff in memory, and then it says, oh, I'm going to write these things now out in sorted order into a segment, a chunk.
Okay, cool. Thank you. Appreciate it.
Yeah. Anybody else?
There's a couple in chat.
Yeah, I wrote those. So LSM is, it sounds very much like how the SQL databases store the tables, is it not? What's the difference?
The in-memory part of LSM can be identical to how SQL stores information.
Okay.
But the disk part of it is very different.
How is that different?
So the disk part is using large ordered log files. Okay. And so there's no tree structure on the disk whatsoever.
Yeah, I mean, database tables, like the actual data is not sorted either, right?
It actually is. So if I had an index, we'll get to relational in just a second, but the basic concept is that my indexing of the information, whether it's using a field in the data as an index, or whether I'm just using, a fake index that I've created on my own.
Yeah.
Ultimately, that index is built into a tree.
Yeah.
And that tree is in sorted order, and that the links that connect the different nodes of the tree are sorting the different pages on the disk. The disks are not physically contiguously laid out necessarily in sorted order,
Yeah.
but
Yeah.
but the data structure is linked in that way.
Yeah.
SS tables
Yeah.
SS tables in an LSM tree are age related, but there is no linking between them. So you could have any kind of random thing in SS tables. So you could have an old SS table that has apple, banana, cherry, and you could have a newer SS table that has, I don't know, Al, Bob, and Charlie. And there's just each individual file is sorted, but there's just no relationship between different SS table segments that are written to the disk.
Well, yes. I wasn't referring to that aspect. I was referring just from a just one table perspective. It's very similar to the SQL databases, just taking one table only.
Okay, I mean, if that helps you think about it, that's great. I think for me, whatever reason, that's not the way I think of it. But yeah.
And also, if we were to just say partition the underlying log file, like sorted is worse than hash indexes. Is that correct? Like if you were to be partitioning the file itself in different computers, then you want random access as much as possible. And so hash indexes would distribute the load better, right?
Not sure. One of the things I actually say at the very end of the notes is that this chapter currently only talks about vertical scaling. So the entire part 2 of the book is about replication, sharding, transactions, and all of those issues. So yes, it's a really good question.
Cool.
I have sort of a broad question on this one. What do you think are takeaway and how valuable do you think this is? Because at least from my perspective, realistically, I'm never going to be making a decision between SS tables and LSM trees. I'm just going to have some database that has already implemented them. So is there really much value in trying to dig in and understand the underlying structure?
I think the author's point is you, thank goodness, won't need to implement one of these unless you just decide it's your love and you want to work for one of these companies. But understanding this will help you decide, should I choose Oracle? Should I choose Cassandra? Should I choose something else?
Mm-hmm.
Right? Because I know underneath the hood what it is that they're doing. Okay. What I would say is that I think that for this case that's covered in just what's covered in chapter 3, LSM trees make a viable alternative to relational B trees. I haven't read ahead far enough to know, but I suspect when you start talking about workloads that have a lot of updates, so a transactional OLTP system, and you want to start doing things like, atomicity, acid guarantees and stuff, that life just is going to get more and more and more complicated with these multiple SS tables and duplicate copies of keys that are, whatever, obsolete. And when you try to do locking, how do you do locking when you've got multiple SS tables that are A to Z? And I just think that you're not. But for an analytic workload, so if you're trying to implement a data warehouse, I could see that alternatives like LSM trees and column stores, because it's primarily read-only. I mean, you have bulk inserts, but you're not doing updates on the fly throughout the day. I think that kind of a workload might get really good horizontal scaling out of this architecture, because B trees are hard to scale horizontally. Well, so we'll see if my prediction's right. I don't know if that's where the author's going to go.
I also think it's really valuable to understand things like clustered indexes versus compound indexes versus primary indexes and stuff like that, even when you're just a developer. And then beyond that, I mean, I'll kind of reiterate what you said, Ted, as well. If your system is going to do mostly OLAP versus OLTP, you might want to lean towards one kind of database versus another. The other thing to take into consideration is, from what I've been reading, if you store information in the cloud services in an OLTP type format, so row format versus a column format, there's a significant difference in the price. Column formats are much cheaper.
That's good. All right, so there's one thing that I wanted to talk about here, which this is where you guys might need to stop me, but are you guys familiar with Bloom filters? Because Bloom filters are really cool.
They're amazing.
And so
No,
I saw
tell us.
this comment in the book. So basically, like if you have a hash table, and let's say you hash to 1 billion different unique values, okay? The odds of 2 different keys just accidentally hashing to the same exact value are 1 in a billion. But if you have 1 million entries already in your hash table, the odds of you hashing to something else that's the same as any one of those, well, now that's dropped to the odds are 1 in 1,000, right? Because you've got 1,000 times as many possible hash values as actual entries. So to Bloom filter, what it does is it does multiple separate independent hashes. And so if you have a 1 in 1,000 chance of the first hash matching, but you do 7 hashes, well, now you've got roughly, things are not necessarily purely statistically independent, but roughly speaking, 1,000 to the 7th power chance that all 7 of them have a collision, even though this key, doesn't actually exist. So when you use a Bloom filter, it's basically just hashing multiple times, and any one of them can give you a false positive because you get a collision. If you get no matches on all 7 of them, then it's a guarantee that this key doesn't already exist in there. If you do see ones in all 7 of your hashes, then it is possible that it's a false positive, but the odds of it are really low. And by configuring the size of your hash and then the number of hashes you do, you can actually design in what level of guarantee you want on the probability of a false positive. So basically, and you can look on Wikipedia, but basically, so Bloom filters are really cool. They take up very little space because they're bitmaps. You only need a 1 or a 0 for each hash. And so the optimization you mentioned is that when you look for a key and it's not in an LSM tree, that's actually the slowest scenario because you are going to search through every single one of your old SS tables. And you can look at the newest one and it's going to say not there. Then you can look at the second newest one, not there. Third newest one, not there, until you go through every single one of them. So finding something, you might get lucky and find it quickly, but something that's not there is always going to be sort of worst case scenario. And so the idea is you apply a Bloom filter up front. And so depending on the Bloom filter, you may have, say, a 99.999% chance that if it's not there, you're going to know it right off the bat, and you don't even have to bother looking at a single SS table. And again, you can design the size of the Bloom filter to guarantee that it's only a 1 in a trillion chance of a false positive, but it's still really fast, even if you are trying to get those kinds of guarantees. Okay, so let's circle back now to B trees. So again, chronologically, B trees came first. In some ways, I think that B trees are more understandable. Just so you know, my notes here are not necessarily exactly in order in the sequence in which the author talked about these, but I've tried to sort of distill the concepts, conceptually. So the big difference here is that B trees, they don't create duplicate entries, but they allow deletes and updates to happen in place. Because of the nature of disks, it's more efficient, instead of storing each record separately, it's more efficient to organize them into pages. Typically what happens is disks are arranged in blocks anyway. And so what you're doing is you're just writing whole blocks at a time. So if you're familiar with trees, right? So reads and writes are logarithmic in time. So on a binary tree, if it's 1,000 entries, it might only be 10 levels deep. And so, the log base 2 of 1,000 is 10. there are these algorithms, there are these data structures that are balanced trees. And so the B in B tree comes from the word balance. But B trees are an extension of balanced binary trees. So instead of having two-way branching, you can have an arbitrarily large number of branches. So the root, instead of having 2 children, it could have 500 children. It could have 2,000 children. And so in practice, if you have a B tree that's branching somewhere between 500 and 2,000 ways at each node, even pretty large databases are actually not very deep. And so you can see that, like, you can have 10 billion entries in a database and only be 4 levels deep. So that's fairly low overhead in terms of adding 4 additional reads just to get from the root to a leaf. And that's without talking about caching and other kinds of optimizations. There is, without going into the gory details about how the algorithm works, but B trees do have this thing where sometimes, if say you're doing insert and the maximum number of records you can hold in one page is 300, if you try and insert a 301st entry, it's going to sort of overflow. And so then what that needs to do is that needs to split that page into 2 pages. And it also pushes activity up to the parent of that particular node. And it can, in the worst case scenario, recursively cause that parent to overflow and have to split, and so on and so forth. But again, if the height of your B tree is 3, 4, or 5, you're really only talking about a worst case scenario of 5 page splits to do one insert. But that is an extra level of overhead that needs to get amortized or needs to get dealt with in terms of your sort of worst case performance. The other big thing about using update in place is that you now have this scary thing about what happens if I'm halfway through some kind of an update, or what if I'm halfway through doing all these page splits and my computer crashes. So you can get inconsistent, corrupted data in your B tree structure. And so that's why every B tree implementation I know of uses a write-ahead log. And so in this case, what you do is you say on the log, here's what I'm about to do. You then, in some way, timestamp it. You go and you make those changes to your B tree, and then either in the log or somewhere adjacent to the log, you say, okay, everything up to this timestamp, I've actually successfully written to the B tree. So what can happen is if your computer crashes, you can actually look at this log and you could say, oh, look, it says everything up till 109 has been written, but there's a couple entries that are at 110, 111. I can actually replay those entries in order to catch up what didn't actually get written to the B tree.
So to kind of add on to that, that's kind of similar how like in-memory databases kind of cover durability, where like in the case where something goes down and memory disappears, then you have this like change log that basically backs up the changes that have occurred. So
Yep.
and I think I've read the part in the chapter where as like the whole part of like writing to disk was that it was durable, and then it was like cheaper than RAM at one point. But as like RAM becomes more cheaper, then that's where like the increase of like in-memory databases became a thing, and how that kind of relates to change logs and what B trees basically utilize, as Ted said.
Yeah, and this chapter, that's a great comment. And this chapter doesn't really go into too much how some of all of this is unnecessary because of how much caching, because of the cost of RAM and in particular fast cache memory has gone down. There's more and more caching available. And so in many cases, when you say, I would like to know the description for product ID 1, 2, 3, 4. You don't actually have to go and search through the B tree. You don't actually have to go to the disk because it's just sitting there in cache. Because 1, 2, 3, 4 is a really popular product. It's just sitting in cache, and so it doesn't go through any of this rigmarole trying to find
Right,
it.
that's where like LLRU caching like plays into a role.
Yes.
But like I guess like I mean, so trade-off is always going to be like an ongoing like theme in this book, where the trade-off is that initially it's going to be expensive because you have to have like the entry point to start the caching, but subsequent reads, since you have the cache, it'll decrease the time it takes for reads.
Yeah.
But like you said, look with RAM becoming more cheaper, which leads to more caching, the need to write into disk becomes less prevalent when you can store more frequently seeked out information through the cache than through disk.
Yep. Thanks. I have a few other notes here just in terms of concurrency control and optimizations. I'm not going to spend too much time on that. So the author talks about some comparisons between B trees and LSM trees. Ryan asked a question. I talked about that a little bit. So I think that if you had an environment that was primarily writes and not reads, then some sort of log-based technology like an LSM tree might actually outperform. I think also for a mostly read-only is where you can try and design things. The reason why you still see relational database systems being very popular is because they are flexible, and I've most of my career been a Microsoft SQL Server guy, and so without going into the gory details, there's just a ton of optimizations that Microsoft has made to improve performance for certain kinds of circumstances. So for example, you can read a ginormous table sequentially from beginning to end extremely quickly in SQL Server because they have these other indexes, this other metadata that tells the system how the data is laid out on disk. That's not just the basic B tree. It's additional data structures. And those are optimized for these other use cases. And so, computers are fast enough that for the common case, you just don't really care about that little extra overhead you have storing these bit maps and extent maps and things like that. But when you have that really heavy duty use case, when you can then, sort of parallelize and pipeline these read operations, that's when you see huge performance boosts from these additional kinds of optimizations. So then there's sort of this next part of the chapter where the author talks about other indexing structures. So Stephen mentioned, so secondary indexes can be very important. I'm not exactly sure how people implement secondary indexes on LSM trees, but for B trees, it's super duper commonplace. And so on an OLTP system, you'll see some indexes. On a more analytical system, you typically will see some secondary indexes on every single table. And so the whole idea is that if you have orders that are sorted by order date, well, maybe you have a secondary index on product ID, maybe you have a secondary index on client ID. And this allows you to very quickly go to items that have particular things. So you can just imagine you write a where clause, you say, show me the stuff, the orders where client equals 1, 2, 3. That's where you may be able to use a secondary index. I will comment without going into too much detail that when you start doing range queries, if you say, give me the 5,000 rows for customer 1, 2, 3, that secondary index might not actually be helpful at the end of the day because you're pulling 5,000 sort of random things. So even though you have this index, just kind of beware that the primary indexes and everything we've talked about here, very high performance, Secondary indexes often don't give you that same kind of bang for your buck. And that's why the author does mention the idea of multi-column indexes and covering indexes, which allow you to skip actually reading full records because all the information you need is contained in the columns in the covering index. We talked a little bit about, you can sort of skip all this stuff and just put everything in memory. So with RAM getting cheaper, some of this is obviated by caching that can happen just sort of behind the scenes. So for example, when you have really large disk caches, you can write software that is dumb and just keeps trying to read from disk, but you'll get really fast performance because the disk cache is going to return the result to you without ever telling the controller to actually go read it off the physical disk. And you don't even know that's happening. So that actually helps a little bit in terms of it's abstracted away from you. You just get better performance from that disk cache, and you don't necessarily have to have all these other data structures and secondary data structures that you're managing and try to improve performance. All right, so let me just pause here before we talk about data warehousing and analytic workloads. Any other things people want to talk about?
Yeah, I wanted to ask, there was something there, can you go up a little bit? It said multi-dimensional indexes. I was wondering, like, because I remember reading from the Microsoft Analysis Server, which is OLAP, it says that it doesn't really need indexes, but then it has this concept called aggregations. And what is these multidimensional indexes that you're mentioning here? Are they the same thing as aggregations, or is it something different?
It's something different. So in this next section about analytic processing, we're going to talk about how you can pre-compute and store aggregations. Like, for example, sums are really common, sales totals, right? I've done some queries that are geospatial queries. So for example, here is an address. What county does this person live in? Okay. And so you have a polygon that defines each county, and you are doing a geospatial intersect to see whether this point, this latitude and longitude, is inside of that polygon.
Yeah.
Okay. For geospatial, you have latitude and longitude, and you cannot just use a traditional A to Z linear index. It's two-dimensional. So that's an example of a multi-dimensional index. And so current versions of Microsoft SQL Server support spatial indexes, which are multi-dimensional.
Okay, which is different from the OLAP aggregations.
Yes. So it's just another complexity, completely different concept.
Yes. Okay, very good. Thank you.
There's also full text indexes. I don't know that much about full text indexes, but again, another slightly different kind of index. All right. Analytic processing, I think most people are probably familiar with that. So I don't know we need to go into too much detail, but so it's pretty common to see you've got your quote unquote production server, that's your OLTP server. And then they're going to say, here's a read-only copy of the data that you can run all of your Tableau reports, big queries, queries, whatever against this second thing. So you can call it a data warehouse, you can call it other names. But the whole point is that this is a duplicate copy of the data. In the old days, you would have fairly stale data. You might say, I only update this warehouse daily, weekly, monthly. Nowadays, people demand stuff, so you see more streaming. But the whole idea is it's a primarily read-only second copy of stuff. The old days, you mostly saw relational schemas. So you see the star schema and if you expand that, the snowflake schema. So there you have large fact tables. And the key thing the author talks about is that a fact table easily could have hundreds of columns. And when you want to know the sales total by region, by store, by department, you really probably only need roughly-ish 4 columns: region, department, store ID, and amount. And so this table might have 400 columns, but if you're only using a handful of those in your query, that's where the conversation transitions to, oh, we could store this data in a columnar way where I store all the amounts physically in chunks, as opposed to these other systems, it's always records that are being chunked together. So when your record is 400 columns wide, it's a really big record, and you only need 4 or 5 of those columns. You're doing a whole lot of you're reading a whole lot of data when actually only a tiny portion of it is the part you really need. So let me see. Other cool things about column stores is there's a lot of compression you can do. So they talk about bitmap coding. I'm very familiar with doing run length encoding. And I believe what Microsoft SQL Server does in column store data is that they will take a really large table and they'll actually break it into chunks. So the whole idea is that you want to have relatively few unique values in a particular column, then you can get really good performance. So if you have a small table, then it's just going to be one chunk. But if you had a table that had, let's say, 100 million rows, then let's say it divided into 25 million row chunks, it can have a separate lookup table for each chunk to say, what are the unique values in column 1 for the first 20 million rows? What are the unique values in column 2? And oftentimes, just due to the nature of these kinds of data, you may have like slowly moving stuff over time. So if the first chunk is 2000, the second chunk is 2001, the third chunk is 2002, you can imagine, for example, product IDs. Certain products didn't exist back in 2000, so you don't need every possible product ID in that column for the 2000 data. You just need the ones that actually existed back in 2000, and vice versa. When you're looking at 2020, a lot of the old products from 2000 don't exist anymore. And so that's a further optimization they do to say that there's fewer unique values in each chunk instead of treating the entire column always as one giant column when you're doing things like the bitmap encoding and the run length encoding. There's a little bit talk about vectorized performance. I'm not that familiar with it, but basically you can do SIMD instructions. And so if you say, I have this contiguous chunk of memory, I want to AND these 100 values with these other 100 values, and they're all loaded in cache, then basically you issue one instruction to the CPU and it will go and internally loop through all 100 rows of that data. And that's going to be much, much faster than you explicitly saying, load the first one, do an AND, load the second one, do an AND, load the third one, do an AND, as individual instructions. And then a few comments on sort order. So you can sort columnar data. And if you do that, then especially one of the benefits you get from this is that first, it allows you to do range queries really easily. But the other thing is that you get really good compression on your sort keys because you're going to get very long contiguous ranges of values. The run length encoding on those things is going to be microscopic in size. And then I was not familiar with this, but the author mentioned this thing called CStore, where we haven't talked about replication yet, but just, you know, if you're gonna wind up storing 5 copies of the data just for redundancy, for protection purposes, what if you did this clever thing and you said the 5 copies can be sorted by different things? So one copy is sorted by store ID, one copy is sorted by department ID, one copy is sorted by customer ID. So then if you say, I want the data where customers 1, 2, 3, then you go to that copy. If you say, I want to know totals of sales for store ABC, then you go to a different copy. So I thought that was kind of a cool, clever idea. Any comments about data warehouses and column stores?
I kind of have a question, but more related to really the AWS kind of ecosystem here. And I don't know, kind of given this background here, does anyone have any thoughts or comments on how you may be using S3, even though S3 is usually considered as like the storage place, but I have seen also almost like increasing kind of a habit of querying against S3 directly, and then what's the relationship between the S3 and Redshift, and then a Postgres database like a little bit downstream. I hope my question.
So I don't know if like Keegan's still on. I think of S3 as a file system and less of a database, but somebody who's more experienced in this, do you have an answer for Becky?
Yeah, so S3 is object storage. So you're storing objects, so like pictures, Word documents, but you can use a service called Athena, which lets you query like a CSV file and run a SQL query on it. I think it's using it's based off a open source tool. I can't remember the name of it. It was something Netflix used. I just, the name's escaping me, but it's using an open source Pesto. That's what it's called. I just remembered it. Presto. I can't remember. It's been a while since I looked at it, but
it's Facebook's Presto.
Yeah, it's so Athena is basically Presto under the hood, and so S3 is still object-oriented storage, but they're basically just doing a managed version of Presto, so you can look at the CSV file, and I guess I don't know what file system they have. I mean, AWS also has traditional RDS instances, so using Postgres and SQL Server, and then they also have like DynamoDB, which is a NoSQL database. They have MongoDB, which is again a NoSQL database. I don't know what file systems they use because they're proprietary and most of them are closed source. But S3 is just object storage. So I don't know. I guess when they use Presto, I don't know how that works. I would.
Yeah. So perhaps super simplistically, I would say I wouldn't think that if you, let's say you were making a competitor to Google Drive, right? And you're going to have millions of users all storing files. You probably can't use S3 natively just by itself. You need something that's going to give you more of a database-like interface for doing reads and writes. And so that's where Presto or something comes in. And obviously then you can also use either a relational database or a NoSQL database as well. Does that make sense?
Right. So S3, we currently actually mainly use it for the reading the CSV file, and actually Athena actually works quite great, exactly like a relational database environment. So we're pleasantly surprised by that. But then my question is, if you think about the cheaper cost the S3 has, right, and then a Redshift at a higher cost, and then a Postgres or RDS incidence, what's really the benefit of, let's say, using Redshift in this case? It's a kind of a column-based kind of a storage format there, but what's really the benefit of using it?
You couldn't use S3 if you had 1 million customers and have nothing else layered on top of it. You would be crushed. The performance would be super duper slow.
It depends what you're doing too. Like, so Athena's really good for if you're doing tons and tons of reads. I'm not sure if you'd run into a performance bottleneck, but it wouldn't be as economically efficient at a certain point. Athena is really good for, hey, we need to do a query, once every day or once every couple days. Then you aren't paying, because for Redshift or Snowflake or one of these other enterprise data warehouses, you're bringing up multiple nodes. You're paying by the hour and you're probably paying for multiple servers by the hour for high availability. So if I mean, it really depends how much data and really how much you're querying it. So I think Athena is actually, if you're just running a couple queries, it's fine. But if you're running, like a query every 10 minutes and you're querying, like hundreds of gigs of data, then it becomes a problem. In S3, there's no limit to the number of files you can put in a bucket, but any individual file can't be more than 5 terabytes. And if it's a 5 terabyte file, it's going to take a very, very long time to upload. AWS and I think other cloud providers, they have ways that you can mitigate this when you upload files. So if you have like a 5 terabyte file, you can actually, they'll send you a box and you can upload the data into this called Snowmobile and Snow.
So Keegan, if you don't mind my jumping in, see, I think you're assuming typical workload. What I'm trying to address in Becky's question is, if you have a database, it's not unreasonable to say you're going to have 100 million entries in there. Okay, you would not put 100 million files all in one single S3 bucket.
True.
That's going to reduce your performance. Okay, because it's not optimized for finding a particular item within a bucket for large N. So then you need somebody else to manage how to divide things up and organize it. And that's where these technologies we're talking about actually do that kind of organization. They could ultimately write their stuff to S3. That's not a problem. I'm just saying that without going into the gory details, if your company has 1,000 files, whatever, just use S3. Don't pay for something else more expensive. But the use cases we're talking about here are where you have things on the orders of millions, billions, trillions. Now you want a database. You want something that's organizing things for you. And then perhaps you want something that allows you to do joins and actually link different pieces of data together.
Right. I think the point is very clear, Ted, on that exact point. I think, and maybe my question here can wait for another discussion. I think at this point we are a little bit wrestling with the various kind of components of the ecosystem, right? So S3 certainly has its purpose and benefits, and then Redshift, and then the Postgres database. So there's some decisions that we kind of need to make, and I'm still very fuzzy about exactly, like, given all, like Keegan's kind of point about, it all depends, like what your applications are, and the size of the data, and the kind of the trade-offs you are making, and all of that. So, but overall, I do have some curiosity around what everyone is using in terms of their overall kind of tech stack at some point, if people can share some of those.
You can.
Yeah, I think maybe we could look at having some conversation along those lines. What I would say right now relative to chapter 3 is, if your data is small enough that you're willing to personally manage it. So when I think about my C drive, I think about folders and subfolders. Okay, you might be doing S3 buckets, and I don't remember the nomenclature for like folders within buckets or whatever. You got 5,000 files, whatever. You want to organize that by different clients, by different whatever projects. Go for it. Just do it. But you are manually managing that. At the point where you say, I don't want to manage it, then you need some other tool. I'll loosely call it a database that manages that for you. Okay. And then you can decide on based on the workload. Again, I'm saying this because just from our past conversations, I suspect that your company's not that big. So you probably do not need some super high-end thing, because you're not dealing with writing thousands, hundreds of millions of things per day.
If the data gets that big, though, you could use Spark on S3.
Right.
So you could do.
I mean, the size is not huge. It's just a couple terabytes of data.
But it's not even the volume. I'm saying the number of things. Right.
Right. But
right. If you have 30 100 gigabyte objects, it's still only 30 objects. You don't need a database to manage them for you. You could just say, here's object 1, here's object 2, here's object 3,
Mm-hmm.
right? But if that whatever terabyte is millions of objects that are small, then you might actually want a database, because it might be a pain for you to be managing folders and subfolders and whatever. Again, that's kind of just at the high level, trying to keep it inside the concept of what we're talking about here, chapter 3.
Yeah. Mm-hmm.
Yeah, Becky, the other thing I would say is be careful trying to copy other companies and other people. Just because they're doing something doesn't mean they're necessarily doing it in an efficient
True.
way. Simply because I've read lots of stories of people who just use lots of Snowflake services, for example. That allows you to be really inefficient at scale, right? It doesn't mean that they're being efficient. They're just clobbering it with a lot of compute power.
Yep. Thanks, Stephen. Okay, so in terms of the chapter material, the last thing this came up, but I didn't realize I didn't scroll. So so just in terms of pre-computing stuff, so you can have materialized views. I've used these fairly often. I have some sort of denormalized flattened data that's in my regular relational database, and so you know, the transactional data may be, you know, 1 row per item purchased, but maybe you just want to say, okay, but if it's like a supermarket, yes, there's 1 row per item, but then like when I, you know, whatever, go to the store, I bought 50 things. So maybe I just want one, I don't know what to call that unit, but, you know, 1 row per, you know, customer going to the store and buying a bunch of things, right? And so I could store the subtotals for each person when they went to the store, instead of having just each individual item, you know, loaf of bread, bottle of milk. And if that's really, you know, requested a lot, then instead of just having a virtual conceptual view, you can have a materialized view. And so you can actually have a second copy of the data that stores, hey, yes, Ted bought eggs, milk, bread, but by the way, that whole thing, when he paid with his credit card, the total was $100. Okay, so you can materialize that. And then the extension of that is you can store different possible subtotals. And that's where there's a 2-dimensional example in the book. In my notes, I tried to do more of a 3-dimensional example where you can have cubes. So again, that's pre-computing totals and subtotals. All right, so then in terms of the summary, relational does updates in place. So that was one of the first questions we got. That's sort of the intuitive way of doing things. You only keep 1 copy, but the bad side of this is it requires random access. Log-based techniques concentrate the writes into fewer sequential chunks, but now you've got multiple copies and you've got multiple data structures, and so you have this complexity, which again, for this use case didn't sound so bad, but when we get to like transactions, then I think it's going to get pretty hairy. You have a data warehouse that maybe you optimize differently in terms of your star schemas, your column stores, whatnot. And then again, we have not really talked about multiple servers and how you implement these things. And so definitely front ends like web servers that are stateless, very, very easy to scale horizontally. When you start dealing with data that has state, then things get trickier. And so I haven't read ahead, but that's where I think things are going to get really interesting in part 2, which is like chapters 5 through, I don't know what, 5 through something, 5 through 10 or something like that. All right, any other comments or questions?
Does Microsoft Analysis Server support materialized cubes?
Yes, so what Microsoft used to call SQL Server Analysis Servers or whatever, OLAP cubes, that was the primary function of that. I don't hear a lot about it these days, so I suspect that other things like scaling horizontally and column stores have sort of gotten most of the attention as opposed to cubes these days.
Yeah.
Anything else?
I have sort of a side comment. I think that for me, it would be useful as an addition to the book, if there was some way that we could have some sort of simulated database, basically, and we say, here's using this technology, here's the performance of these various different queries and use cases, and then here's a comparison using an alternative. And then if we could compare between the two, and we could say, oh, look, because of this implementational detail, there's this hotspot in the queries or something like that. I think that that would add a lot to the learning for me.
Okay.
But I don't know.
Not sure how easy that is to do, but I will definitely keep in mind in terms of if the book doesn't have clear examples of like contention, hotspots, difficulties, when we talk about the different distributed systems, then I think, yes, that will be very helpful to go through examples. I know we're already like way over time, but one of the things I did add to the content here is, and if some people need to leave, I understand, but I just wanted to do a very simple case study about SQLite. This is about as simple as you can get, just to show how even the concepts in chapter 3, without talking about too much else, when you're talking about a real world implementation of one of the simplest possible databases, there's still extra levels of secondary indexes and abstractions and things that need to be dealt with. And so, you know, it's horrible when people ask, well, what should I do about this? And the answer is, it depends, right? It depends on your workload. It depends on this, whatever. But these are the reasons why, unfortunately, it's really difficult, because there's just so many complexities. So for those of you who can stay, SQLite, it's super simple database. It's just one single file that gets stored on your disk. Okay, it is not a client server technology. It just completely, you know, runs. I don't know how to say it. This may not be exactly the right way to say it, but it runs in the thread, in the process of your application. It just becomes part of your application. There's very little concurrency supported. So if anybody needs to do a write, they lock the file, and that locks everybody else out. Nobody can do a write, nobody can do a read while you're doing a write. But multiple reads can happen concurrently from different threads. That's a tiny little bit of concurrency. So you can store data in there, and there's some other things in terms of like views and whatnot, but triggers. But we talked about these briefly. It does support full text indexes and spatial indexes. So there's already some complexity in terms of what kind of data is in there. There's regular data, there's regular indexes, there's full text spatial indexes. And the storage is pretty straightforward. Every table is a B tree. So if you have a client's table, it's a B tree. If you have a products table, it's a B tree. All the indexes are B trees. And there's one special table called SQLite master, and that lists all of your objects. So it lists all the tables, all the indexes. It also lists anything else you have. It lists triggers, it lists everything. So if we stopped here, we would say, this sounds like a pretty simple thing. In terms of chapter 3, it's using B trees. It's not using LSM trees, it's just using B trees. But if we use the author's very loose terminology of index of any other kind of metadata, then you start to see that there is other data that SQLite either has to or wants to keep track of. So one thing it has is, it has to understand the concept of unused, fragmented, free memory within the file. So it has to have a free list, okay, where it keeps track of pages that don't actually have anything in them. So you delete something, and now you delete a table, and now there's, you know, pages that aren't used anymore, they go onto the free list. It has this concept of pointer maps. So in a tree, parents point down to children. In B tree, it's not required that children point back to their parents, but these pointer maps actually create the reverse pointers. And this is used if you're trying to defragment the file. So if you're trying to get rid of that empty space and cluster stuff together. Within each B tree page, there are headers that need to be updated whenever you do any kind of update or write or delete or whatever. That might not cost you too much because you're tending to write to the disk the entire page and the header's part of the page. But nevertheless, there's a little bit of compute overhead. And there's also this indirection because we talk about things being sorted. So within, the leaf of a page, you might say, oh, well, this page has A through B. And so it has, AAA at the beginning and, BZZZ at the end. But the reality is nobody actually stores things in that order. And so there's actually this pointer array that says logically they should be in this alphabetical order, but physically we stored them in the page in wherever. And so there are these other data structures. And so this is why the devil's really in the details. So even something as super simple as SQLite has all this extra overhead, data structures, compute that's going on to manage what's got to be just about the world's simplest possible real. I looked on Wikipedia. It says SQLite is the 6th most commonly used database. So this is a real system. This is not a toy made up thing. This is used by various products and operating systems and whatever, certain versions of iPhones or whatever, like actually used this. But again, even as simple as it tries to be, and it is pretty simple, but there's still sort of this other stuff. And so this stuff affects how it actually performs under various workloads. So it's not just the theoretical performance of B trees. There's this other stuff on top of it. And that's why it's so, unfortunately, so much of it depends. You need to really deeply look at your workload. And this is even before you think about caching, which can happen outside of SQLite again. So anyway, just wanted to kind of add that as a way of highlighting why it is, unfortunately, there aren't good answers that says, hey, if you do this, just use product A. If you have that, just use product B. It's just hard.
Yeah, Ted, I've been waiting all my life for that. Who's going to tell me that?
Well, I will use my rule of thumb, okay, which is if you're not really big and don't have an extreme use case, whatever you choose, don't choose something expensive.
I know. I think probably this is a conversation for another time. I'm still trying to get my heads around whether or not we're big or small and why is it just seems there's a lot of complexity in what we do. And that actually leads me to one question for, since everyone or most of everyone here do a lot of this kind of data science stuff. I'm just curious, like we just talked about this database and how the different formats and whatnot, but let's just say that machine learning, one of the good things that it can deal with is that a lot of the features that you're inputting into the model. So in your actual work, let's say you need to really take in a data file that has lots of features, but isn't that those features are technically like the columns in the tables, or are you guys really having a different kind of structure to take in the data? I'm just very curious. Like if we're not talking necessarily about images and stuff like that, right? If we're talking about more or less like tabular data, in my mind, I just don't know how you guys are connecting to tables that are feeding these, could be thousands of features into the model, but then how do you store it? How do you kind of, make it effective?
I don't know if somebody else has a comment. I would say my rule of thumb is store everything as additional features, keep going wider, wider, wider until something breaks and it forces you not to. But yeah, if you can, just keep adding features.
Gotcha. And any other opinion? Because there's like Redshift has a 1600 column limit. So you technically and like I said before, our survey data set, a single data set can have 9,000 columns. I mean, that's a different topic, like why we have so many, but I'm just saying, we may not have a ton of data compared to other companies, but we do have a fairly kind of a peculiar situation here.
Are you normalizing your data? Like, and I don't mean normalizing in the machine learning perspective, but normalizing in a data modeling perspective.
Exactly. Like,
And I don't know how to
many
answer
of
that
those
question.
many of those are probably binary features that represent categorical variables. So like for multiple choice questions, you'd have a different binary column for each one.
Right.
And
I think,
that's
yeah.
an inefficient way of databasing it. It's a
Mhm.
it's a very efficient way of doing machine learning on it. So you want to use the right format for what you're trying to do.
Right, but technically you are still, you still need to store the data in the, like each column, even if we like transform those, but each column still represents a one possible feature, so to speak, right? And
Right.
if, let's say we do have lots and lots of questions, like I said before, we could have like 50-minute survey, which kind of translates into a lot of questions per record. And we have a number of years of data, right? Let's say 5 years of data about how people like certain movies and stuff like that. So it doesn't sound like a very complex issue, but in reality, it just it is a very slow.
It may have been made complex by someone doing the data engineering and not doing it well, by not normalizing the data, like what Keegan said. That does not sound like to me a lot of data, and it should be possible to store that data efficiently within the limits of most modern database systems.
Yeah, so I would say I would store that information on disk in a relational way, and it would reduce the amount of size. And it's clearly more data than you can sort of eyeball, like imagine an Excel spreadsheet. It's more data than you can eyeball at a time. But basically, if you don't get past, I'll say randomly, 10 million, it's not big. For a computer these days, anything less than that it's just not big. So, and like a pandas data frame, by the way, is a column store. So physically, it's stored, the columns of stuff are all together. So yeah, I don't know. I don't really care if you have 1,000 or 5,000 columns in my mind.
And I like Ted's approach to starting small. Just start with some number of features and work your way up, and don't worry about it until it breaks. And then you can start figuring out how to be more optimal in which columns you're using for your modeling, and then maybe doing some PCA, maybe doing some data normalization.
Yeah.
We'll
definitely do that. Yep.
Right. So Becky, just adding on to what the guys are saying. So you would work forwards and then backwards again, right? So forwards, you would start off with whatever was in your data store, S3 or relational database or whatever. You might expand that out into more columns, and I'll pick an easy one, right? So you might have a date column, and in order to figure out your model, you might expand that date column out into, the month of the year, the day of the week, the day of the month, all that sort of stuff, right? And then you would feed that into your model. Eventually, you'd come up with a model, right? But it may turn out that model doesn't really care about most of those columns. So then you'd end up throwing them away, right? In the final thing. So that's what I mean by you work forward, as Ted was saying, kind of just keep expanding and adding more columns kind of thing. And then once you figured out what the model actually needs, which is what Hobson is saying, then you just, re-optimize down to just the things that you need to be feeding into your models.
Yep, it makes sense. I think I'm just curious, like what would be like, do you guys have any sort of this kind of challenges with dealing with lots of features being fed into the model at the same time? Like,
this is the quintessential challenge of data science. See, it's the challenge of data engineering. Everybody from a beginner working with a small data set deals with it, to professionals dealing with large data sets. It's not a large data set problem. It's just the problem of doing feature engineering. And so, because if you have a small computer, or you're trying to do it all in RAM, or you're trying to do some recommendation engine that requires you to have all the columns, it can be hard even with small data sets. So you have to get really good at choosing the right features.
Yeah, but I will say that I haven't heard anything yet, Becky, that says to me that you couldn't just brute force this in the most obvious representation. Now, it might be slightly faster if you did A or you did B, but will it actually just work if you just say, hey, I just want rows and columns, and just, I think it should.
Right. That's the main direction we're heading right now. Yep. Mm-hmm.
If you want to try this, so there's some really good plugins for pandas that use like H5 files or other formats that don't actually pull it all into RAM. So if it doesn't all fit into RAM and you can't do just standard pandas, you could even just use pandas with one of these wraparounds. I forget what they're called. But
Yeah, like I'm learning a lot about Dask these days, but basically, that's what I'm saying is just keep doing the easy, simple, straightforward thing until it breaks. And then if it breaks, ask, is there some really simple thing I can do, like change my import, and so say dask.readcsv instead of pd.readcsv, and that solves your problems. Great. And then if that breaks, then you're like, crap, now I actually need to figure out if I'm going to use Spark thing or some other thing or whatever, and then you need to actually like make the effort.
Is there someone actually solving problems with your data, Becky, or is this just a theoretical? Sometime down the road, we might consider doing this.
I think right now it's a little bit theoretical right now. But for example, I mean, this is a forever question, right? Like how can we predict the box office performance better for any given movie? And you could introduce all kinds of features to it, and we continue to collect data and all of that. So yeah, and the data can be, consumers' feedback, or it can be a ton of metadata about the cast, about the director, about everything about this movie.
Yeah, I mean, again, for me, my sort of keep it simple rule of thumb, right, is just do it easy, just keep adding features. If you're like, it works, but it's kind of slow. I mean, if you're paying some analyst, on the order of 100K a year, like buying a really fast computer for 10K is nothing compared to, the cost of labor, right? So if you can just keep solving your problems easily just by not having to think about it and just throw a little bit of hardware at it, I would say it's a very reasonable approach until you can't. It's broken, it just won't work.
It's not a good idea to try to anticipate all the problems before you just dive in and do it. Agile has proven to be the only way to do any kind of software development, data science, or anything. Just do it, and if it becomes a problem, fix it.
Got it. Thank you.
All right. Well, I appreciate so many of you are still with us. Was there anybody else who wanted to ask a question or make a comment? This is, again, in case anybody joined in the middle. So we are going to take a 2-week break over the holidays. Our next chapter discussion will be January 9th. So certainly, again, we'll be on Slack if you want to ask questions either as you're reading the book or about stuff we've already covered. But hey, now's your chance if you want to ask something before we go.
Ryan dropped a very interesting link to the ranking of popular databases. It's a lot of fun. So while it is open, look at it. I mean, the chat.
I can repost that in the Slack too. It is pretty interesting to see because they also have it split by the various different types. So if you want to see what the most popular graph database or time series or document or whatever, you can sort by that too.
Yes, I was surprised that among document database, MongoDB is the best, very high, very far from everybody else.
Yeah, it doesn't necessarily mean that it's the best, but it's the most popular right now, which might mean it's the best. It might just be that it's been around.
It might mean the people who bought Mongo X years ago haven't gotten rid of it yet. But SQLite on that's only what, number 9 or something like that. So not quite as high as what Wikipedia said, but still, it's up there. It's not fake. It's You know, it's really used inside of products.
It's only 2 ahead of Microsoft Access, though, which is like something to.
Okay, well that's a fair criticism. I hate Access.
But I do wonder why Redshift is so low, though.
What is low, Becky?
Amazon Redshift.
Oh, I think
competition. I mean, Snowflake really owns the data warehousing market right now. I mean, Snowflake's a lot more expensive, but when most companies switch to a data warehouse in the cloud, they use Snowflake.
Yeah, so you've got competition between AWS, GCP, Azure cloud environments. Then you've got competition from third-party vendors, and I think to a certain extent you have competition from other Amazon products.
Yeah.
Where people maybe could use Redshift but use some other AWS option.
I'm looking at their methodology for determining this score, and one of them is basically mentions on Stack Overflow. So it might actually be that being a very difficult to use database increases your ranking because a lot of people are asking questions about it. I don't think that's necessarily the case, but it could be an interesting way to.
Yeah, so SQLite could be underrepresented because it's easy.
Yeah.
It's the same reason why JavaScript was more popular than Python. It's just, anyway, yeah, be careful. Popularity isn't a good thing.
But it certainly does give us an idea. Oh, sorry, go ahead.
On an FAQ database, it's a bad thing.
On some of the cloud databases, Google Cloud just released, well, actually it did just release, it released this earlier this year, back in January, but you can now run BigQuery cross-cloud. So you can run their BigQuery engine on like AWS S3 and I think on AWS Redshift, even though it's a Google Cloud product, and also on Microsoft Azure. So, but with data warehousing, even though they're proprietary, like Google's allowing you to go cross-cloud.
So I also have a quick question here. So looking at Cassandra, which it says here is a Y column store, is that, can that be interpreted as an opposite of Amazon Redshift type of store?
Well, Redshift is still SQL database and Cassandra is NoSQL, so it's not only SQL. I'm not familiar exactly with Cassandra's query language. I think it looks like SQL, but it can do things that SQL can't do. I don't think it's relational, but
gotcha.
I'm not going. I don't know enough about it to comment.
Cassandra's weird. I'm planning on reading more about it throughout the course of this book. It is definitely not a vanilla anything. It is not a vanilla B tree, and it is not a vanilla column store. So, so just like I sort of did this case study for SQLite, I don't know if I'll present it, but certainly, it's up there. It has some real performance. That's why people have used it, but it's complicated.
A question for you. You mentioned something about the pandas data frame and the underlying storage type. I'm trying to find resources online, but I don't see anything mentioning how is it actually stored in memory.
Oh, I was just simply commenting that if you have a pandas data frame and it's got 12 columns and 100 rows, okay, that what that really is 1,200 item column stores. Okay, so it is column oriented first and then row oriented second. Visually, when I look at it like I do ahead of the first 5 rows, I think in my brain about it being row oriented, maybe because I'm a database guy historically, right? But that's not the way it's physically stored. So from an efficiency perspective, you can think of it more as a column store.
It's
Are
not
you thinking of it, or is it a resource that you have in mind? That's what I was trying to find.
the physical storage is not at all related to the API. So just because the column is first doesn't mean it's storing it that way, because you can do a dot transpose on a data frame and that's 0 time, and it doesn't move anything in RAM. And so switching columns.
So sorry, yes. So I'm talking about the default. Actually, I don't know, George. I mean, I've gotten this all like verbally. I don't know. I haven't looked for documentation on the default pandas implementation, but Hobbs is right. The implementation is not required, it's not guaranteed, and that's how Dask is able to sort of swap in, and cuDF is able to just swap in, because they say, hey, as long as you know, when somebody says merge, you do a merge, and when somebody says whatever square brackets, you pull out the requisite subset, right? You can store it any way you want, and there's like sparse implementations, right? So I should be careful. So I'm just talking about the default implementation, the vanilla one, when you just take regular pandas and you just create a simple little data frame.
I have to look at the code, I guess.
Yeah, I, as some people may know, I like to comment and joke about it. So I started as an R guy. There's clear documentation on the R side that says that R data frames are columns, and it's just a list of columns. There's very loose, very little relationship between columns. Now you can actually have 2 3-dimensional matrices or whatever, that's slightly different, but data frames. And pandas was sort of modeled after R data frames, but you're right, I haven't actually seen like a Medium article that says, hey, in case you're wondering, this is how pandas default implementation stores data.
That's what I was looking for online. I couldn't find it.
But you know, pointers are stored next to each other. In C, anybody ever worked with C pointers?
Mm-hmm.
Okay. Well, they're stored next to each other. You can actually, if you want, from a data frame, if you want some particular indices, you can actually go to pointers and to say that you want pointers from this one to this one. But the pointers themselves are not values.
Yes, I'm simply saying that if you had a data frame with 20 columns and 20 rows,
I know how it works in R. I even know that the matrix in R is actually one vector.
Right,
and,
but I'm not talking about matrices, I'm talking about data frames. So I mean, I could write a little bit of code
yes,
to time
but
it, but if you
underneath the Python and underneath R, we have C.
Yes, and so what I'm saying is that if you said, pull me 20 values from the same column, it's going to run faster than if you say, pull me 20 values from the same row.
Yes.
Even if you use whatever, like iloc. And so the conceptual syntax is the same. You're just saying 0 through 19 on this axis, 0 through 19 on that axis. It is column stored in nature. All right, thanks guys. Anything else? Any other questions or comments? Are you guys liking this book so far?
Yes.
I think this chapter is most above my head right now. Maybe from all these trees structure, I think it's really above my head, but it's okay. I will just keep listening to you guys.
Well, weren't you with us when we did support vector machines?
Well, I would say at least on that side, I conceptually I can understand what's going on, and here it's hard for me to think about all this indexing in certain way. Yeah, that's a block for me in my brain.
All right, so maybe for future chapters, like Ryan was saying, specific case examples and actually showing the diagrams maybe is a good idea.
But you guys have been great. You and Ryan are both very good teachers.
Thanks, Becky.
Here, here.
All right. Well, again, thanks for those of you who stuck with us for the discussion. I always enjoy the discussion, and I always learn things. And I appreciate everybody who's helped answer other people's questions. That's a huge benefit. So I think we'll call it officially a wrap here. And then if any people want to stick around, then we can talk a little bit about Kaggle competitions. But we're again way off the timeline. So thanks. Good seeing everybody.
Happy holidays, everyone.
Happy
Yeah,
holidays.
happy holidays.
Happy holidays, everyone.